Electricity is the closest thing we have to a modern miracle. It powers hospitals, it moves money, it keeps water flowing through cities. And yet, in some of the most advanced countries on Earth, the lights still go out. Not just during storms, not just during disasters. Blackouts happen in systems designed for stability. So the real question is not how power grids work, it's why they fail. Because when you look closely, the weakness isn't technical, it's structural. To understand that, we need to understand one uncomfortable fact. Electricity is not stored at scale in most grids. It must be generated and consumed at the exact same moment, every second. If demand rises suddenly, supply must rise instantly. If supply drops, demand must drop. The grid is a constant balancing act. That balance is measured in frequency. In most of the world, 50 or 60 Hz. If the frequency drifts too far, systems shut down automatically to protect equipment. That's when blackouts begin. So grids are not static systems. They are live organisms, constantly correcting themselves. And that correction costs money. Power grids are built around one primary goal: reliability. But reliability is expensive. It requires redundant capacity, reserve margins, maintenance crews, upgraded transmission lines, modernized substations, backup generation. None of these things are visible to the average voter. You only notice the grid when it fails, which creates the first structural problem. Maintenance is politically invisible. Replacing aging transformers does not win elections. Upgrading transmission lines is not glamorous. Investing in redundancy does not create headlines. But deferring those investments saves money in the short term. And short-term cost efficiency is often rewarded. Most utilities operate under regulated frameworks. They are incentivized to keep costs low, avoid rate increases, show operational efficiency. In many systems, profit margins are tied to capital investment, not long-term resilience, which creates a subtle tension. Investing in reliability increases costs today, but the failure risk might not materialize for years. And when it does, it can often be blamed on weather, demand spikes, unprecedented events. The system rarely fails because engineers don't understand physics. It fails because reliability competes with cost. And cost usually wins until it doesn't. Now add a second layer. Modern electricity demand is changing. Electrification is accelerating. Electric vehicles, heat pumps, data centers, artificial intelligence infrastructure. Peak loads are increasing in many regions, and peak demand is the most dangerous demand. Grids are not built for average usage. They are built for extremes. The highest demand hour of the year determines capacity planning, which means infrastructure must be sized for moments that may last only days. That's expensive. So systems often run closer to their limits, not because engineers want them to, but because overbuilding capacity is hard to justify economically. There is also the issue of transmission. Electricity is often generated far from where it is consumed. Power must travel across long-distance transmission lines. Those lines are expensive to build. They require land approvals, environmental review, political cooperation across regions. In many countries, building new transmission can take a decade. Demand, however, can grow much faster. So grids become congested. Congestion increases fragility. Then there's redundancy. In theory, every major component should have backups. In practice, redundancy costs money. Utilities must decide, do we build a second line? Do we upgrade this transformer early? Do we maintain older infrastructure more aggressively? Each decision competes with budget constraints, and budget constraints are influenced by regulators, politics, and consumer pressure. Consumers want low electricity bills. Reliability costs raise bills. The trade-off is rarely discussed openly. When blackouts happen, the explanation often focuses on the immediate trigger: a winter storm, a heat wave, a wildfire. But those events are stress tests. They reveal underlying fragility. In 2021, Texas experienced one of the most severe blackouts in modern American history. A winter storm pushed electricity demand to extreme levels. Heating systems switched on across millions of homes simultaneously. Meanwhile, parts of the generation fleet began to fail. Natural gas infrastructure froze. Some power plants went offline. Supply dropped just as demand surged. The system could not maintain balance. Frequency began to fall. To prevent total collapse, operators initiated rolling outages. From the outside, it looked like a disaster. But structurally, it was a stress test revealing trade-offs. Texas operates a largely isolated grid, designed to reduce federal oversight and maintain market flexibility. That structure limits the ability to import large amounts of electricity from neighboring states during emergencies. Reserve margins had been optimized for efficiency, not extreme cold events. Winterization requirements were limited. None of these decisions were irrational. They were cost-benefit trade-offs. The storm did not create fragility. It exposed it. A resilient system can absorb stress. A cost-optimized system struggles. The difference is not intelligence, it is incentive alignment. Now consider one more pressure. Modern grids are becoming more complex. Distributed generation, intermittent supply sources, digital control systems. Complex systems are harder to manage. They require faster response mechanisms, better forecasting, more coordination. Complexity itself is not the problem. But complexity without aligned incentives increases risk. If coordination is fragmented across multiple private and public entities, decision-making slows. If investment responsibility is unclear, upgrades stall. And when accountability is diffused, resilience weakens. So why do power grids fail? Not because we lack engineering knowledge, not because electricity is mysterious, but because reliability is expensive, maintenance is invisible, redundancy looks wasteful, and peak capacity is politically difficult to justify until the lights go out. Then suddenly, reliability becomes priceless. But by then, the structural decisions were already made. Power grids are not fragile by accident. They are optimized systems operating under economic and political constraints. The blackouts are not random failures. They are the visible result of invisible trade-offs. And those trade-offs are written in the fine print. Nothing is random. Nothing is neutral. Read the fine print.